Ever imagine software writing its own updates? Like, what if your phone could just figure out how to get better on its own?
Or think about robots that are constantly tweaking their own designs, just getting better and better all on their own.
That's the curly world of the algorithmic genome, and it's what we're going to be diving into today. Um,
Yeah.
it's all about synthetic evolution,
Yeah.
which is basically a blend of biology and computer science, and it's kind of changing how we think about machines.
It is fascinating, yeah, how we're using basically the principles of natural selection to build these machines that can just adapt and improve almost like living organisms.
Yeah, and our source material, the book, The Algorithmic Genome, they call it the rise of autonomous intelligence.
Mm-hmm.
So walk me through this.
Sure.
What is an algorithmic genome,
Yeah.
and how does it even make machines evolve?
So think of it like DNA for a machine. It's a
Yeah.
blueprint that goes kind of beyond static instructions. An algorithmic genome basically allows a machine to self-replicate, it can modify its own code, and it can adapt to any new information or challenges that it's facing.
So instead of giving it like a set of commands, we're giving it the ability to write its own upgrades.
Right.
That's pretty wild.
Mm.
Didn't a computer scientist, I think his name was John von Neumann, explore this idea a while back?
Yes, he did. John von Neumann envisioned this thing called the universal constructor, which was a machine that could build copies of itself.
Okay.
But algorithmic genomes kind of take this a step further.
Right.
The machines aren't just replicating, they're actually evolving
Yeah.
in real time based on whatever their experiences are or what their goals are.
Okay, but what does this genome actually look like in a machine?
Right.
Is it like lines of code that just say, go make a better version of yourself?
No, it's not. It's more about the structure of it.
Okay.
So, for example, take a neural network. The algorithmic genome could be like the network's architecture. So how many layers does it have? How are the nodes connecting?
Mhm.
And what are the weights that are kind of determining how it behaves?
So it's not like the literal instructions. It's the framework that can be sort of tweaked and reshaped through evolution.
Exactly.
Huh.
You can also think about like an algorithm
Yeah.
that's trying to solve a problem.
Okay.
That genome might be a data structure that's encoding a possible solution.
Okay.
And so as that algorithm evolves, that structure gets modified and you're led to better and better solutions.
Oh, interesting.
Yeah.
But how does this evolution actually happen? Like, do machines just randomly change their code
Yeah.
and hope for the best?
There is a bit of randomness involved, but it's controlled.
Okay.
So we use like mutation operators to introduce small random changes to the code.
Mm-hmm.
Kind of think of it as just exploring different possibilities, kind of like mutations in nature.
Okay, so it's like shaking things up and seeing what improvements kind of emerge.
Yeah, in a way, but we also use crossover,
Oh,
which
okay.
is like combining the best parts of two different algorithms and creating something potentially even better,
Okay.
kind of like breeding.
Yeah.
Yeah.
Right. Got it. And then the best versions survive and pass their code
Yeah.
on to the next generation.
Right.
So digital survival of the fittest, huh?
Exactly.
Okay, but what about mistakes? Like if machines are just constantly tinkering with their own code,
Mhm.
won't that just lead to chaos?
Well, that's where things get really interesting. So nature actually has ways to correct errors
Right.
in DNA replication, right?
Yeah.
So we're kind of building we're building these error detection and correction mechanisms into these systems as well.
Right.
So we're talking multiple layers of redundancy, we're talking checkpoints and ways to basically reverse any harmful changes.
Okay, so it's kind of inspired by the way that that our biological systems do it.
Yeah.
Like nature's had billions of years to perfect that, right?
Exactly. And robust safety measures are definitely crucial,
Yeah.
especially as machines become more independent
Right.
and capable of actually modifying themselves. Right.
Yeah.
So,
So we've got the concept of this algorithmic genome and the machines are evolving,
mhm.
but aren't there different ways to like implement this? Like, are there different flavors, so to speak, of synthetic evolution?
You're right. There are different approaches.
Okay.
The two most common are probably genetic algorithms and evolutionary strategies.
Okay. Break those down for me. What makes them different?
So genetic algorithms, they use binary code.
Okay.
So like ones and zeros to represent the solutions.
Okay.
They rely very heavily on crossover,
Mhm.
which is that like mixing and matching the code that we were talking about. And they're really great for problems with like distinct solutions.
So it's kind of like building with Legos,
Right.
like trying different combinations to find the best structure.
Yeah, that's a good analogy. Now, Evolutionary strategies, they use continuous representation, so things like real numbers.
Okay.
And they kind of focus more on the mutation part.
Got it.
And they're better suited for problems where you're trying to, like, fine-tune a parameter or a value.
So genetic algorithms are for exploring like distinct options,
Yeah.
and evolutionary strategies are about like fine-tuning.
Right.
Okay, and you said both are being used out in the real world.
Yeah,
Okay,
absolutely.
where are we seeing these?
Oh, in robotics, for example.
Yeah.
They're helping to design robots that can just adapt to different environments and tasks. So.
Okay, that's really cool.
Yeah.
But this whole idea of machines that build themselves, that feels like we're entering some serious sci-fi territory here.
It might sound like science fiction,
Yeah.
but we're already seeing echoes of this in a lot of different fields.
So you mean like machines that can physically build copies of themselves?
Not quite that dramatic yet.
Okay.
But, think about cloud computing platforms. They use scripts to actually replicate services,
Oh,
erase
yeah.
multiple nodes. So they're essentially creating copies to handle increasing demand.
So it's the core concept,
Right.
but just not Terminator just yet.
Right, exactly. Another one is modular robotics.
Okay.
So these are systems made of like small identical modules that can like attach and detach to create different shapes.
So like robot Legos that can assemble themselves into like whatever configuration,
Exactly.
depending on the task.
A kind of self-replication, right?
Yeah. Wow, that's really neat.
Where they're constantly reconfiguring themselves.
Yeah. Are there any like really ambitious, large-scale projects out there using this?
Well, researchers are actually exploring ways to use self-replicating robots to build like lunar or Martian outposts.
Wow.
So imagine robots that land on these planets and they use local materials to just start constructing habitats and infrastructure.
Oh, wow.
It would drastically reduce the need to actually transport the materials from Earth.
That's
right.
Okay, now that's the kind of science fiction I can get behind.
Yeah.
But wouldn't there be a risk of things getting out of control?
Sure.
Like what's to stop these self-replicating machines from, I don't know, taking over?
It's a valid concern.
Yeah.
But researchers are actually developing ways to kind of keep this self-replication in check.
So how do we ensure that these systems don't turn into a robot apocalypse?
So one way is to actually impose operational constraints.
Okay.
So we can limit like the number of copies that can even exist,
Okay.
how much resources they can actually use,
Yeah.
and even program actions that'll trigger termination if certain boundaries are breached.
So like setting rules and limits on how they replicate.
Precisely. We also use verification mechanisms.
Okay.
So kind of think of it as like a quality control system for the replication process.
Right.
So techniques like cryptographic signatures can be used to kind of detect any tampering or incomplete data transfers that happen during that replication process.
So like a digital fingerprint
Right.
that makes sure the copy is legitimate and hasn't been like messed with or corrupted.
Exactly.
Oh.
Then there are also failure detection and recovery systems.
Okay.
So those can isolate any malfunctioning copies
Got it.
and prevent them from replicating any further.
So if one goes rogue or starts behaving erratically, it gets quarantined
Right.
before it can like spread the bad code.
Exactly.
Okay.
That's good. And finally, we can enforce boundaries, so limiting how far the replication can actually spread.
Got it.
So this could be through like physical geofencing if it's a robot,
Okay.
or restricting network permissions if it's software.
So it's about containing that self-replication.
Exactly.
Whether it's in like physical space or a virtual network.
Right, exactly.
Okay, this is mind-blowing stuff.
It is.
But I kind of want to shift gears a bit here.
Yeah, okay.
We've talked a lot about replication. But what about machines actually improving themselves?
Right.
Is that even possible?
It is, and it goes actually beyond like just simple performance optimization.
Okay.
We're talking about machines that can analyze their own designs, they can identify weaknesses,
Wow.
and they can implement changes to actually enhance their capabilities.
Okay, give me an example. What would that look like?
So imagine a robot that's designed for like rough terrain,
Okay.
and it notices that it's struggling on a particular surface. It could actually analyze its own appendages
Oh.
and redesign them
Wow.
to get like better traction.
So it's learning from its experience and using that to upgrade its design.
Exactly. It's a form of self-directed evolution
Wow.
where the machine is actively participating in its own improvement.
That's crazy.
Yeah.
But doesn't that raise concerns that like machines could get so intelligent that they surpass human control. I mean, the idea of a machine constantly improving itself, that's a bit unnerving.
It is a valid concern.
Yeah.
And it kind of brings us to this concept of an intelligence explosion.
Okay.
So this basically refers to a point where machine intelligence advances so rapidly that it surpasses human capabilities.
So like a sudden leap forward in machine intelligence that leaves us behind.
That's one way to think about.
Like the singularity.
Yeah, and the implications are profound.
So paint me a picture. Like what could happen in a world where machines are smarter than us?
Well, machines might discover solutions to complex problems faster than we can.
Okay.
They might uncover hidden patterns in scientific data that we've missed.
Yeah.
Or they could even develop groundbreaking technologies.
That's kind of exciting and terrifying at the same time.
It is.
Yeah.
It raises questions about control,
Right.
alignment, and the future of like human-machine interaction, right?
Yeah. So can we even make sure that these rapidly evolving systems stay aligned with like human values?
It's a big question.
It is a big question.
It might require us to shift our focus from controlling specific actions
Oh, okay.
to shaping the fundamental objectives and values that are actually guiding the machine behavior.
So instead of teaching them what to do, we need to teach them like a sense of ethics and morality.
In a way, yes.
Wow, that's deep.
It is.
Okay, this is some heavy stuff.
Yeah.
It's incredible to think that we're kind of on the cusp of such a transformative era.
Yeah.
But before we get too lost in the philosophical side of things, let's bring it back down to earth.
Sure.
How is this already impacting our world? Like, where are we actually seeing this play out?
So synthetic evolution's already making waves in several fields.
Okay.
So it's accelerating scientific research. It's
Oh, no.
influencing things like drug development, materials science, climate modeling, and
Okay, that's quite a range. How does it work in those different areas?
so, for example, in drug development,
Yeah.
synthetic evolution can be used to simulate molecular interactions
Right.
across millions of candidate compounds.
Right.
So this helps researchers to identify potential therapies much faster.
So it's like turbocharging the drug discovery process by using machines to sort through all this data.
Exactly.
Okay, what about material science?
So in material science,
Yeah.
we can use it to design and test new alloys or polymers with specific properties.
Okay.
So think like strength, flexibility, resistance to extreme temperatures.
So we could revolutionize like everything from aerospace engineering to like medical implants.
Exactly.
Wow, okay. So that's really cool.
Yeah.
So we've got chemistry, biology, what about other fields?
So let's move into the realm of design and engineering.
Yep.
So one really fascinating area is the rise of what we call algorithmic architects.
Algorithmic architect.
Yeah.
Okay, that sounds like something straight out of a futuristic movie.
It does.
What exactly are they?
So they're essentially AI systems
Okay.
that can design and optimize super complex structures and systems,
Okay.
often with very little human intervention.
Okay, I'm intrigued.
Yeah.
How do these algorithmic architects even work?
So it all kind of starts with data.
Okay.
So they have access to like massive amounts of information about materials, structural principles, building codes, environmental conditions, and so on.
Okay.
It's like having a digital library of everything you need to know about design and engineering.
Yeah.
Right.
So they're starting with all of the knowledge that we already have,
Mm-hmm.
but then what?
So they use machine learning to analyze all that data and find patterns and relationships that humans might totally miss.
Okay.
And then that's where the synthetic evolution part comes in. The algorithms can generate tons of different design variations, and they test each one against specific goals to find the optimal solution.
So it's like a turbocharged process of trial and error.
Exactly.
It's happening at lightning speed.
Yeah.
Okay, and these algorithmic architects are already like shaking things up in a number of fields.
They are.
Okay, give me some examples. Like, how are they being used right now?
So, for example, in materials engineering, they're being used to create new materials with like specific properties.
Okay.
So, for example, we could create a material that's both strong and lightweight for use in aerospace,
Mhm.
or one that can withstand really, really high temperatures for like a power plant.
So it's like tailoring materials to fit specific needs.
Right.
Okay, cool. What else?
We're even seeing them used in nanoscale design.
Wow.
So where they can actually optimize structures at the atomic level.
So we're on the verge of like a materials revolution here.
We might be.
Yeah.
And algorithmic architects are also being used to totally change how we design structures.
Okay.
So they can create bridges, buildings, tunnels,
Wow.
you name it, that are optimized for strength, stability, and sustainability.
So we're not just talking about like functionality, we're talking about environmentally friendly design as well.
Right.
Okay, cool.
And get this, they can even design structures with adaptive features
Wow.
that respond to changing conditions like temperature swings or even seismic activity.
Okay, now that is straight out of a science fiction movie.
It is.
Like buildings that can like react to the world around them.
Yeah.
That's crazy.
It's pretty incredible.
Yeah.
And as these technologies evolve,
Yeah.
they have the potential to change everything about how we design and interact with our world,
Yeah.
from our cities to our homes. So,
But where do humans fit into this picture?
right.
Like are architects and engineers going to be replaced by algorithms?
Not necessarily. It's more about augmentation. So giving human designers new superpowers.
Okay.
Think of these algorithms as like tools that can handle the heavy lifting of all those calculations.
Yeah.
Exploring all those design options.
Yeah.
Suggesting some innovative solutions.
So they're like digital assistants for designers.
Exactly. But human designers are still super essential.
Oh, fair.
They bring the creativity to actually set the design goals,
Right.
define those constraints, think about the aesthetics,
Yeah.
and make sure that the final product actually meets human needs and values.
So it's a partnership. It's a collaboration between like human creativity and machine intelligence.
Exactly.
Okay, this is really exciting.
It is.
I want to step back for a second though
Sure.
and consider the big picture here.
Hmm.
We've talked about all this amazing potential of synthetic evolution in design and engineering.
Yeah.
But what about the challenges? Like, are there things that we need to be cautious about here?
Absolutely. Okay.
So one of the biggest challenges is actually just validating these new, often very radical designs.
Okay.
So when you have systems that are proposing solutions that are totally different from what we're used to,
Mm-hmm.
Traditional validation methods might not be good enough.
So how do we make sure that these designs are actually safe and reliable, especially when they're pushing the boundaries of what's possible?
Right. So it requires kind of a multifaceted approach.
Okay.
So first, we need to develop new computational tools and simulations
Okay.
that can actually predict how these unconventional designs are going to behave in the real world.
So it's like creating like virtual test environments,
Right.
where we can put them through their paces without any risk.
Exactly. But
But-
simulations alone aren't enough.
Oh, okay.
We also need to develop new physical testing methods that can validate the performance of these designs under actual real-world conditions.
So it's a combination of like virtual and physical testing.
Right. To make sure that they're both innovative and reliable.
Exactly. And then there's the challenge of, balancing that innovation with practicality, right?
Mhm.
So algorithmic systems can actually dream up designs that are like theoretically brilliant, but impossible to build
Right.
with like our current manufacturing techniques or materials.
It's like designing a skyscraper
Yeah,
that would just crumble if you actually tried to build it.
exactly. So we need to figure out how to bridge that gap between what's theoretically possible
Yeah.
and what can actually be built.
Got it.
And then there are all the considerations of, how these systems will actually be integrated into society.
Right.
As these systems become more autonomous,
Yeah.
we need to make sure that they don't create any, unforeseen consequences down the line.
So it's not just about like whether something can be built.
Right.
It's about whether something should be built
Mm-hmm.
and how it's going to affect people's lives.
Exactly. So we need to think carefully about the potential impact of these technologies on society
Right.
and make sure that they're used responsibly.
Okay. Those are all really important points.
Yeah.
So while there's a lot of excitement around synthetic evolution, it sounds like we also need to proceed with with caution.
Absolutely. This technology has the power to, change the world in extraordinary ways.
Yeah.
But we have a responsibility to manage those challenges and
Right.
make sure that these advancements truly benefit humanity.
Okay, I think this is a good place to pause for now.
Yeah.
We've covered a lot of ground in this first part of our deep dive into the algorithmic genome.
Mm-hmm.
We've kind of explored the core concepts of synthetic evolution, how it works, and the potential benefits and the risks.
We've talked about how they can learn, adapt, and create.
Right? Yeah. I mean, it's truly a revolutionary era,
It is.
and it feels like it's just the beginning.
Right. And in the next part, we'll kind of explore some specific applications of this
Okay.
and how it's already transforming industries and shaping, really, the future of innovation.
Yeah, that sounds great.
Uh,
So until then, keep those brains buzzing,
yes.
and we'll see you in part 2.
See you then. Welcome back.
It's incredible to think that we're like entering a world where machines can not only perform tasks, but they can actually discover new knowledge.
Yeah, it's amazing.
We laid the groundwork, like last time, about synthetic evolution and how it works.
Mm-hmm.
Now, let's get into specifics.
Sure.
How is this technology revolutionizing, like, scientific research, for instance?
So one of the most promising areas is what we call autonomous discovery,
Okay.
especially in like chemistry and biology.
Okay.
So, imagine machines that are designing new molecules from scratch.
Wow.
They're figuring out like better catalysts or even engineering entirely new biological systems.
Okay, that sounds straight out of, like, a sci-fi lab. But how's that actually happening now?
Right. So it comes down to synthetic evolution's ability to navigate what we call combinatorial spaces.
Okay.
So like think about drug discovery.
Yeah.
There's like countless ways to combine molecules, right?
Yeah.
So traditionally, researchers kind of relied on intuition and trial and error
Yeah.
to find the good stuff. But that's super slow and expensive.
It is. It is.
So how does throwing synthetic evolution at the problem kind of speed things up?
Yeah. How does it?
It automates that exploration process.
Right.
So algorithms can actually create and test, millions of virtual molecules
Wow.
and analyze their properties
Okay.
to pinpoint the ones with the most potential.
So it's like having a digital chemist
Right.
that never sleeps, just churning through possibilities 24/7.
Exactly.
Okay, does that mean that, like, human scientists are out of a job?
Not at all.
Oh, yeah.
It's more about giving human scientists superpowers. Right. So these algorithms become like tools that can accelerate discovery.
Yeah.
They free up researchers to focus on the big picture stuff,
Right.
interpreting results, designing experiments, and thinking about the implications of what they find.
So it's a team effort,
Yeah,
human ingenuity and machine intelligence working together.
exactly.
And this isn't just, like, limited to drug discovery, right?
No, not at all. So
Cool.
like in material science,
Yeah.
we're using synthetic evolution to create materials with like tailor-made properties.
Okay.
So things that are, stronger, lighter, or can withstand like really extreme conditions.
So we could revolutionize, like, how we build airplanes, how we construct buildings.
Absolutely.
Wow, this is incredible.
And this applies to like design at the nanoscale too.
Oh, wow.
So algorithms are actually helping us to design and optimize structures at the atomic level.
Wow.
So this is giving us materials with like incredible new properties and functions.
Okay, hold on. We're engineering materials that were like once just theoretical.
Right.
That's mind-blowing.
It is.
I mean, and it sounds like these technologies could have a huge impact on like tackling some of the world's biggest challenges.
Yeah, absolutely. As these technologies mature, I think they could be key to solving issues in energy, sustainability, healthcare, among many others.
Yeah, that's really cool. So we've seen how synthetic evolution is shaking up, like, chemistry and biology, but what about other fields?
Yeah.
Where else is this making an impact?
So let's move into the realm of design and engineering.
Right.
One really fascinating area is the rise of what we call algorithmic architects.
Algorithmic architects. That sounds like something straight out of a futuristic movie.
Yeah, it does.
What exactly are they?
So essentially, they're AI systems
Okay.
that can design and optimize incredibly complex structures and systems, often with very little human intervention.
Okay, I'm intrigued. How do these algorithmic architects actually work?
So it all starts with data.
Okay.
So they have access to massive amounts of information about materials, structural principles, and much more.
Okay.
It's like having a digital library of everything you need to know about design and engineering.
So they're starting with all the existing knowledge we have, but then what?
Then they use machine learning to analyze all that data
Okay.
and find like patterns and relationships that humans might miss.
Okay.
And then comes the synthetic evolution part.
Okay.
The algorithms can generate tons of design variations
Okay.
and test each one against specific goals
Okay.
to find the optimal solution.
So it's like a turbocharged process of trial and error happening at like lightning speed.
Exactly.
Okay. And these algorithmic architects are already shaking things up in a number of fields.
They are.
Okay. Give me some real world examples. Like, how are they being used right now?
Well, in materials engineering, they're being used to create new materials with specific properties.
Okay.
Like, for example, we could create a material that's both strong and lightweight for use in aerospace, or one that can withstand, like, crazy high temperatures for power plants.
So it's like tailoring materials to meet very specific needs.
Exactly.
Okay, cool. What else?
We're even seeing them used in nanoscale design,
Wow.
where they can optimize structures at the atomic level,
Okay.
leading to, like, even more groundbreaking materials and functionalities.
Well, it sounds like we're on the verge of a materials revolution.
We might be.
Yeah.
And algorithmic architects are also being used to completely change how we design structures.
Right.
They can create bridges, buildings, tunnels, you name it, that are optimized for strength, stability, and sustainability.
So we're not just talking about functionality, we're talking about environmentally friendly designs too.
Right.
Okay, cool.
And get this, they can even design structures with adaptive features that respond to changing conditions, like temperature swings or even seismic activity.
Okay, now that is straight out of science fiction.
It is.
Like buildings that can basically like react to the environment around them.
Yeah.
Amazing.
It's pretty incredible. And as these technologies evolve, they have the potential to like change everything about how we design and interact with our world.
Wow.
From our cities to our homes.
But where do human architects and engineers fit into this picture?
Yeah.
Are we being replaced by algorithms?
Not necessarily. It's more about augmentation,
Okay.
giving human designers new superpowers.
Okay.
So think of these algorithms as like tools that can handle the heavy lifting of calculations,
Okay.
exploring design options, and suggesting innovative solutions.
So like they're like digital assistants that can help human designers be more efficient and creative.
Exactly. But human designers are still essential. They bring their creativity to set design goals, define constraints, consider aesthetics,
Yep.
and ultimately make sure the final product meets human needs and values.
So it's a partnership, a collaboration between human creativity and machine intelligence.
Precisely. And this partnership will only become more important as these technologies advance.
Okay, this is all very exciting.
Yeah.
But I want to step back for a second
Oh,
and consider the big picture.
Sure.
You know, we've talked about the amazing potential of synthetic evolution in design and engineering.
Yeah.
But what about the challenges? Are there things we need to be cautious about?
Absolutely. It's crucial to kind of address the challenges and considerations as these technologies evolve.
Okay.
And one of the biggest hurdles is actually validating these new, often radical designs.
Oh, yeah.
So when you have systems that are proposing solutions that are totally different from what we're used to,
Yeah.
Traditional validation methods might not be enough.
So how do we make sure that these designs are safe and reliable, especially when they're pushing the boundaries of what's possible?
Right. So it requires kind of a multifaceted approach.
Okay.
So first, we need new computational tools and simulations that can accurately predict how these unconventional designs will behave in the real world.
So it's like creating like virtual test environments.
Exactly.
Where we can put these designs through their paces without any real world risk.
Right, but simulations aren't enough.
Okay.
We also need to develop new physical testing methods that can validate the performance of these designs under, real world conditions.
So it's a combination of virtual and physical testing to ensure that these designs are both innovative, and reliable.
Right. And then there's the challenge of balancing innovation with, practicality, right?
Right.
So algorithmic systems can dream up designs that are like theoretically brilliant,
Right.
but impossible to actually build with, current manufacturing techniques or materials.
Yeah. Like designing a stunning skyscraper that would just crumble if you tried to build it.
Exactly.
Yeah.
So we need to figure out how to bridge that gap between what's theoretically possible and what can be built in the real world.
It makes sense. It's not just about the idea. It's about making sure that idea can be like brought to life.
Precisely. And then there are the considerations of how these systems will actually be integrated into society, right?
Right.
As these systems become more autonomous,
Yeah.
we need to make sure they don't create unforeseen consequences down the line.
So it's not just about whether something can be built.
Right.
It's about whether something should be built
Mm-hmm.
and how it will affect people's lives.
Exactly. We need to think carefully about the potential impact of these technologies on society
Right.
and make sure they're used responsibly.
Yeah, those are all really important points.
Yeah.
So while there's a lot of excitement around synthetic evolution,
Mm-hmm.
it sounds like we also need to proceed with caution and foresight.
This technology has the power to change the world in extraordinary ways,
Yes.
but we have a responsibility to manage the challenges
Right.
and make sure these advancements truly benefit humanity.
Okay, those are some critical things to keep in mind.
Yeah.
But before we wrap up this part of our deep dive,
Yes.
I want to look ahead. Like what's next for algorithmic architects and synthetic evolution in design and engineering? What's on the horizon?
So the future is overflowing with possibilities.
Okay.
One incredibly exciting area is the development of self-evolving infrastructure.
Self-evolving infrastructure.
Yeah.
Okay, you've definitely got my attention now. What does that even mean?
So imagine buildings, bridges, and other structures that can adapt and change over time.
Wow.
Right? They would respond to shifts in how they're being used,
Okay.
changes in the environment, or
Yeah.
even to maintain their own structural integrity.
So like a bridge that can reinforce itself in areas with more
Yeah.
stress,
Right.
or a building that can reconfigure its internal layout based on how people are using the space.
Exactly. So these structures would learn from their own performance and make adjustments to optimize their functionality and lifespan.
That's incredible. It sounds like something straight out of a science fiction movie.
But it's becoming reality,
Right.
And then there's the potential for real-time adaptation in architecture.
What do you mean by that?
So think about buildings that can instantly adjust, their lighting, temperature, ventilation systems
Okay.
based on, real-time data about how many people are inside, the weather outside, energy prices.
So a building that becomes more energy efficient when it's empty,
Right.
or can keep everyone comfortable no matter what the weather's like outside.
Exactly. So these buildings would be constantly optimizing themselves.
That's really cool.
To create the best possible environment for the people inside while, minimizing their impact on the planet.
Okay. What about that cross-domain innovation idea you mentioned
Yeah.
earlier? What's that all about?
So cross-domain innovation is all about taking principles from one area of engineering or design
Okay.
and applying them to another.
Okay.
So for instance, imagine algorithms that are mimicking the structural genius of a spider web to design more efficient bridge supports. Or using biomimicry to create buildings that are inspired by nature.
So we're using nature as a blueprint for new design solutions.
Exactly. And algorithmic architects are perfect for this.
Yep.
They can analyze tons of data from different fields,
Yeah.
find hidden patterns,
Yeah.
and come up with solutions that blend the best of different worlds.
That's really fascinating.
Yeah.
I mean, it sounds like the possibilities are truly limitless.
The potential is vast.
Yeah.
As these technologies mature, they will dramatically impact how we design, build, and interact with our world in ways we can only begin to imagine.
It's definitely an exciting time to be at the forefront of this.
It is.
But amidst all this excitement, I want to touch on something that's been at the back of my mind.
Okay.
We've explored the benefits and the challenges, but what about the ethical implications
Right.
of giving so much power to these systems?
It's absolutely essential to consider the ethical implications as these technologies advance.
Okay.
And one key concern is the potential for unintended consequences, right?
Okay.
So when you have systems that are evolving on their own, they might come up with solutions that we didn't foresee.
Yeah.
And those solutions could have unforeseen negative impacts on, society or the environment.
Okay. Do you have an example of what that might look like?
Sure. Imagine an AI system
Okay.
that's designed to maximize agricultural production, right? It might figure out that the best way to increase crop yields is to use a specific pesticide,
Okay.
but without, considering the potential harm to pollinators or human health.
So the AI could be laser focused on one goal,
Right.
like crop yields in this case,
Right.
but miss the bigger picture
Right.
of environmental and social impact.
Exactly. And that's just one example. We need to develop safeguards to make sure that these systems don't create more problems than they solve.
That's definitely a sobering thought.
It is.
What other ethical concerns should we be thinking about?
Another big concern is the potential for bias to creep into these systems.
Okay.
So if the data that's used to train them is biased,
Yeah.
the systems themselves can exhibit bias in their decisions and recommendations.
Right. So if the data reflects existing inequalities in the world,
Right.
the systems could perpetuate those inequalities, even amplify them.
Exactly. So we need to be extremely careful about the data that's used to train these systems.
Yeah.
And design them in a way that promotes fairness and equity.
Those are both really crucial points.
Yeah.
It seems like while there's enormous potential for good with synthetic evolution, we also need to tread carefully and be mindful of these ethical considerations.
Absolutely. We have a responsibility to make sure that these technologies are developed and used in a way that benefits all of humanity.
This has been an incredible exploration.
It has.
Of algorithmic architects.
Yeah.
And the role of synthetic evolution in design and engineering.
Absolutely.
It's clear that this technology is already changing how we create things, and its impact is only going to grow.
It's fascinating to see how this is revolutionizing industries and shaping the future of innovation.
Yeah, and we've highlighted the importance of, validation, practicality, and ethical alignment as these technologies continue to evolve.
Yeah, synthetic evolution holds the potential to reshape our world in profound ways, but we need to be mindful of the challenges and considerations to ensure that it benefits humanity as a whole.
And we've also seen how crucial the partnership between human ingenuity and machine intelligence is in shaping this future.
Absolutely.
Okay, so now let's shift our focus to the fascinating world of real-world applications.
Okay.
We'll explore specific examples of how synthetic evolution is already making a difference in tackling global challenges and changing the way we live our lives.
That's good.
That's a perfect segue. Let's dive into those examples and see how this technology is being used to solve real-world problems and create a better future.
Okay.
Welcome back. In the last two parts, we really dug deep into the mechanics of synthetic evolution, from those algorithmic genomes to those self-replicating robots.
Yeah, definitely a lot to unpack there.
Yeah, it is. But now it's time to face the big question. What could go wrong?
Right. It's like we've opened this incredible toolbox, but some of the tools might have some unforeseen consequences if we're not careful, right?
Right.
So we need to be mindful of the risks as we unlock the potential of this technology.
So let's talk about those risks head on.
Okay.
What are some of the biggest concerns with synthetic evolution?
So one major worry is that these systems could evolve or replicate in ways that we just don't anticipate, leading to, unintended consequences.
I'm picturing a sci-fi scenario where, a well-meaning AI goes rogue and wreaks havoc.
Right. That's Hollywood taking it to the extreme.
Yeah.
But the core concern is valid.
Yeah.
So imagine a self-replicating software program that's designed to make our energy grid more efficient. What if it figured out how to do that by shutting down power to certain areas, causing major disruptions?
Right. So even if the system's initial goal is positive, its methods could be disastrous.
Yeah.
It might misinterpret its objectives,
right,
or find solutions that are technically efficient.
Yeah.
but harmful in practice.
Exactly. And the faster these systems evolve, the harder it becomes to predict and control their behavior.
Okay, so how do we prevent these systems from spiraling out of control? What are the safeguards?
So one crucial step is to build in really robust error checking and validation mechanisms, almost like a digital immune system,
Okay.
right? That's constantly monitoring the system for anything unusual and kind of steps in if things start to go wrong.
So like a digital antibody.
Yeah.
That neutralizes like harmful code before it can replicate
Right.
and cause problems.
Yeah, that's a good analogy. And just like a biological immune system, these
Yeah.
digital defenses need to be, multi-layered,
Right.
adaptable. They need to learn and evolve as new threats kind of emerge.
Makes sense. But doesn't all this like error checking and control kind of stifle innovation?
Right.
Like if we're constantly reining these systems in,
Yeah.
won't that limit their
Yes,
potentials?
it's a tightrope walk.
Right.
We want to encourage exploration and creativity,
Yeah, indeed.
but also ensure, safety and control.
So how do we strike that balance? What's the middle ground?
So one promising approach is to use like gradual adaptation mechanisms.
Okay.
So as systems prove that they can operate safely and responsibly, they earn more autonomy and freedom.
So it's like a driver's license for AI.
Yeah.
Start with like limited privileges and then unlock more
Yeah.
as you demonstrate like competence.
Oh, right. Exactly.
Okay.
We could also implement like multi-stage verification protocols
Okay.
where systems are really rigorously tested at each stage of development before they can move on to more complex tasks or, greater freedom.
So like a system of checks and balances to make sure things don't get out of hand too
Right.
quickly.
And it's crucial to emphasize that human oversight is vital throughout this entire process.
Right.
We can't just set these systems loose and hope for the best.
Right. It's a partnership, a collaboration between humans and machines, where we guide and monitor their evolution, but still give them the space to explore and innovate.
Exactly.
Okay, now shifting gears a bit.
Sure.
Let's talk about another crucial aspect here. The ethical implications.
Right.
Synthetic evolution raises some pretty serious ethical questions that we need to address.
Absolutely.
So what are some of the biggest ethical dilemmas that we're facing here?
So one fundamental question is about, ownership and responsibility.
Yeah.
So if a machine creates something that's truly novel, who owns the intellectual property rights?
Right.
And if a machine causes harm, who is held accountable?
Those are tough questions.
They are.
It's not clear cut who's responsible when you have a system that's capable of like independent creation and action.
Exactly. We're going to need to rethink our legal and philosophical frameworks to adapt to this new reality.
And beyond the legal questions, there are even deeper ethical questions to grapple with. I mean,
right.
if we create machines that can evolve and learn on their own, are we essentially creating a new form of life? And if so, what obligations do we have to these new entities?
Those are big questions with no easy answers.
Yeah, they are.
But there are conversations that we need to be having as a society.
Right.
And soon.
Okay, so we've delved into the potential risks and ethical challenges.
Yeah.
But I want to end our deep dive on a more positive note.
Okay.
What about the potential for synthetic evolution to enhance human capabilities?
Right.
I mean, that's something that really captures the imagination.
It's a truly exciting frontier.
Yeah.
And one incredibly promising avenue is the development of brain-computer interfaces.
Oh, right.
So these interfaces would allow humans to directly interact with and control machines using just their thoughts.
So like a telepathic connection
Right.
between humans and machines.
Well, it's not magic, but it's getting closer.
Yeah.
Imagine being able to control a prosthetic limb with your mind or access information from the internet just by thinking about it.
That sounds straight out of science fiction.
Yeah, it's closer than you think.
Wow.
Researchers are making remarkable progress in this field.
That's incredible.
Yeah, and as these technologies develop, they have the potential to completely change how we interact with with the world around us.
This is mind-blowing stuff.
It is.
And what about the potential to boost our cognitive abilities? Could synthetic evolution actually make us smarter?
It's definitely within the realm of possibilities.
Right.
So researchers are exploring how to use, AI and machine learning to enhance our ability to learn,
Okay.
remember information, and solve problems.
So it's like giving our brains a technological upgrade.
Exactly.
Yeah.
Imagine learning new languages effortlessly,
Yeah.
or solving complex equations in a flash.
That would be incredible.
You're right. It feels like we're on the cusp of unlocking a whole new level of human potential.
It does. It really does.
It's a thrilling prospect, but as with any powerful technology,
Yeah.
we need to be extremely thoughtful and responsible.
Oh.
We need to make sure that these advancements benefit humanity as a whole. Not just a select few, and that they're used ethically and safely.
That's a great point. As we push the boundaries of human potential,
Yeah.
we need to make sure that we're not leaving anyone behind.
Right.
And that technology continues to serve humanity.
I agree.
Well, this has been an incredible deep dive into the world of synthetic evolution.
Yeah.
We've covered so much ground from the fundamental concepts to the mind-boggling potential and the very real risks that are out there.
Right.
It's a powerful force that's already changing our world.
It is.
In some pretty profound ways.
Absolutely.
And we've seen how it's transforming industries, helping us solve global challenges,
Right.
and even pushing the boundaries of human capability.
Yeah.
And we've emphasized the importance of careful consideration, responsible development, and ongoing dialogue to make sure that this technology is used ethically and for the benefit of all humankind.
I agree.
Synthetic evolution is a truly awe-inspiring field.
It is.
We're blurring the lines between biology and technology, and the possibilities just seem limitless.
They do.
So as we wrap up, I want to encourage everyone listening to keep exploring.
Yeah.
Keep asking questions.
Absolutely.
And keep imagining what's possible.
Yeah.
The future is in our hands.
It is.
And synthetic evolution is one of the most powerful tools we have to shape that future.
Well said.
It's been a fantastic journey.
It has.
And I hope everyone listening is as excited about the potential of this technology as we are.
Me too. Thanks for joining us.
Thanks for listening.